Let's do an example to see how one would solve for the mixed strategy Nash equilibria of a game. Here we're going to look at a game where two players are playing tennis, and we'll look specifically at a situation where player 1 is serving and player 2 is returning the serve. Player 1 can either serve to player 2's backhand, to his forehand, or he can just serve in the center. Player 2 can anticipate that player 1 will serve to his backhand and move to the left. He can anticipate that player 1 will serve to his forehand and move towards his forehand. Or he can anticipate that player 1 will serve down the center and just stay there. We can see the payoffs that they get from the choices that they make. They have to make these choices simultaneously. Player 1 serves, and as player 1 is serving, player 2 has to anticipate which way the serve is going to go. We'll just look at a few examples of the payoffs. If player 1 serves to the forehand, and player 2 correctly anticipates and moves to his forehand, he'll be able to hit the ball straight down the line for a winner, and he'll win the point, and he gets 5. If player 1 serves to the forehand, but player 2 stays put in the center, then the payoffs are 2 for player 1 and 3 for player 2. This reflects that there's some chance that player 1 is going to win the point, and there's some chance that player 2 is going to win the point. Another example is if player 1 serves to the backhand, but player 2 moves to the forehand, then player 1 wins the point and he gets a payoff of 5. To solve for a Nash equilibrium in mixed strategies, one has to first eliminate any strictly dominated strategies. And we go through iterated removal of strictly dominated strategies, and once we can't do that anymore, we then try to calculate the probabilities on the remaining strategies. Let's start with the fact that F is strictly dominated for player 1. How do we see that F is strictly dominated? If player 2 plays F, then both C and B give higher payoffs than F, because you get payoff of 0 from playing F, whereas you get a strictly positive payoff from playing C or B. So both C and B give you a strictly higher payoff from playing F. So no matter which of C and B you play, you get a higher payoff than you get from playing F, should player 2 play F. If player 2 plays B, then the payoff player 1 would get from either C or B is at least as high as the payoff he would get from playing F, and as long as the probability that he plays C is higher than 0, then his payoff from randomizing between C and B would be strictly higher than his payoff from playing F, which would be 2, because randomizing between 2 and 3 with at least some positive probability Q on 3 would give you Q times 3 plus 1 minus Q times 2, which has to be bigger than 2. Finally, we look at this part. Let's suppose the probability that B is played is 1 minus Q. Then as long as 1 minus Q is big enough, then the payoff from randomizing between C and B is going to be greater than 2, because the payoff from B is higher than 2. How big does 1 minus Q need to be? The payoff from randomizing between C and B when player 2 plays C is Q times 0 plus 1 minus Q times 3, and we need that to be at least 2. So 0 plus 3 minus 3Q is 2, so Q has to be smaller than 1/3. So for any Q between 0 and 1/3, the strategy 0, Q, 1 minus Q strictly dominates F. So Q has to be strictly bigger than 0, and it has to be strictly less than 1/3 to ensure that this mixed strategy strictly dominates F. But since we can find such a mixed strategy that strictly dominates F, F is strictly dominated, so we can remove it. But once we know that player 1 is never going to serve to player 2's forehand, player 2 can eliminate moving to his forehand from his strategies. He doesn't have to worry about moving to his forehand either. Why? Because then, once we've eliminated F from player 1's strategies, staying in the center dominates moving to his forehand. If player 1 plays C, payoff from moving to forehand is 3, staying in the center is 5. If player 1 plays B, payoff from moving to the forehand is 0, the payoff from the center is 2. In either case, 5 is bigger than 3, 2 is bigger than 0, so C dominates F. So we can remove F from player 2 strategies. That leaves us with this reduced game. Now it's clear to see that neither C nor B dominates the other for either player. From player 1, 3 is bigger than 0, but 3 is bigger than 2. For player 2, 5 is bigger than 2, but 2 is smaller than 3. So neither C nor B dominates the other for player 1 or player 2. Is there a pure strategy equilibrium here? Let's check. If player 1 plays C, player 2's best response is to play C. But if player 2 plays C, player 1's best response is to play B. So it can't be a Nash equilibrium for player 1 to play C. What about for player 1 to play B? If player 1 plays B, player 2's best response is to play B. But if player 2 plays B, player 1's best response is to play C. So playing B for 1 can't be a Nash equilibrium either. So there's no pure strategy Nash equilibrium here. Since there's no pure strategy Nash equilibrium, we're going to have to find a mixed strategy Nash equilibrium. Let Q be the probability that player 1 plays C, and 1 minus Q be the probability that he plays B, and let P be the probability that player 2 plays C, and 1 minus P be the probability that player 2 plays B. We can now solve for what P and Q need to be. So let's suppose sigma 1 star, sigma 2 star is a Nash equilibrium. Then sigma 1 star has to take the form 0, Q, 1 minus Q for some Q, because we know that F is strictly dominated. And sigma 2 star has to take the form 0, P, 1 minus P for some P, because we know that F is also strictly dominated for player 2 once we've removed F for player 1. The way we're going to solve for P and Q is to write down the expected payoff for both players 1 and 2 from either of the strategies and set them equal to one another. So 1's expected payoff from playing C is the probability with which player 2 plays C times the payoff that player 1 gets when they both play C, which is 0, plus the probability that player 2 plays B times the payoff that player 1 gets when player 2 plays B and player 1 plays C. That's just 3 minus 3p. Similarly, his payoff from playing B is p times 3 plus 1 minus p times 2, which is 2 plus p. For 1 to randomize, he has to be indifferent between playing B and C. So 3 minus 3p has to be equal to 2 plus p. Solving for p is a quarter. We do a similar analysis to find what q has to be. We find that 2's expected payoff from playing C is 2 plus 3q, and B is 3 minus q. Again, player 2 has to be indifferent between the two if he's going to randomize. So 2 plus 3q has to be equal to 3 minus q. Solving for q is also a quarter. So we've solved for the Nash equilibrium, and that Nash equilibrium is for both players to play forehand with probability 0, center with probability quarter, and backhand with probability 3/4. So the general steps for solving these games, like we just did here, is to first eliminate strategies that are not rationalizable. So first, you perform iterated removal of dominated strategies. Second, write down all the indifference conditions. Third, solve for the probabilities. One thing I should make clear here is that in this particular game, it was relatively easy. There were only 2 remaining strategies. And if there's no pure strategy equilibrium, then you have to put positive probability on both strategies. But if there are many remaining strategies after you've performed IRDS, then you have a problem that could be somewhat complicated computationally. You don't know a priori which strategies are going to have a positive probability. So you have to try all different combinations. And that's why this problem of solving for the Nash equilibrium of a game is actually a computationally hard problem. Nonetheless, even though it can be hard to calculate, every finite game has at least one Nash equilibrium. Nash proved this in his very famous paper. You can look at the citation in the textbook and have a read if you're mathematically more inclined. It's a very elegant and fairly short proof, but we won't get into that.